Welcome back to this course on polymer chemistry, and in today's lecture, which is lecture number 17, I am going to cover or begin our discussion on ionic chain polymerization. Now, in this lecture I plan to discuss the general characteristics of ionic chain polymerization, and while discussing I will compare how this ionic chain polymerization compares with radical chain polymerization, and then we will go to cationic chain polymerization and talk about different types of initiation for cationic chain polymerization, and then go to propagation and termination reactions in cationic chain polymerization, and then I will talk about kinetics of cationic chain polymerization and then energetics of cationic chain polymerization, and in next lecture I plan to talk about the other type of ionic polymerization, which is anionic chain polymerization. Now, let us begin our discussion on ionic chain polymerization. Now, as the name suggests, in this case the initiation is from a anionic species, whether it is a cation or anion. Say if I consider M as a monomer and I is the initiator, then it could be a cation or a anion, which will according to which we name cationic polymerization or anionic polymerization. It could be acceptance of electron giving rise to a radical anion, or removal of a electron which gives you radical cation, which two of which might combine to give you a dianion or a dication, which can further initiate the chain reactions from both the sides. So, this is a case of cationic polymerization, this is a case of cationic polymerization, and these two are the case of anionic polymerization. And in this case the ionic species are the initiator, or rather the initiators are ionic species, so as the propagating species are also ionic. Now, there are some polymerization, for examples initiation by coordination or say metal oxide, which also progress through a ionic species and propagates through ionic species route, but those we are not going to cover as a ionic chain polymerization. So, ionic chain polymerization we will consider only when both the initiation and the propagation reaction is by ionic species. Now, like radical chain polymerization, these ionic chain polymerization reactions are not very popular commercially. There are two main reasons why they are not so utilized commercially. One is that stringent requirement of polymerization in case of this ionic polymerization, it require very stringent conditions which are difficult to achieve in a large industrial scale, and also this ionic polymerization are very selective, which means that not every monomers can be polymerized by ionic polymerization, like unlike radical case where most of the monomers, double bond containing monomers can be polymerized by radical chain polymerization mechanism. So, these are the main two reasons why this ionic chain polymerization are not practiced that commercially in that scale, and so it is in that sense is not that important like radical chain polymerization. However, this polymerization, this ionic chain polymerization gives us opportunity to synthesize specialized polymers like block copolymers or telecally polymers, which are basically oligomeric type polymers, oligomers having functional groups at the end of the chain, which we can be utilized further for another reaction. So, let us start discussion on ionic polymerization, and let us talk about first the general characteristics. And while talking these general characteristics of ionic polymerization, we will compare its differences or its likeliness with the chain radical chain polymerization. First is that, as I just said, that it is much more selective, much more selective. Now, while we started our discussion on chain polymerization, we talked about that these monomers like this ether, which have electron dominating group, like their oxygen, which can be lone pair can be donated if it has a cationic center here. Now, this type of monomers can be polymerized by cationic chain polymerization reaction, because the resulting cationic propagating semi can be stabilized by the electron donating mechanism donation by the oxygen atom here. Now, for anionic chain polymerization, we need to have monomers which have electron withdrawing group, which could be, as we discussed earlier, something like this acrylonitrile or acrylates or methacrylates and so on. This can be polymerized anionically, because the resulting anion can be stabilized by the resonating with this carbonyl bond. So, in that sense, this anionic and cationic polymerization are very selective, and only if the monomers with weak inductive effect and ability to stabilize the propagating species by resonance, both for cationic and anionic, then these monomers can be polymerized by both cationic and anionic. So, if I want to complete this sentence, inductive effect and ability to stabilize both cationic and anionic propagating species. For example, you have a styrene where both cation and anionic can be stabilized by resonance with this aromatic group, or say a diene 1,3-butadiene, where a cation resulting cation or anionic can be stabilized by resonance from this double bond. As you see, we have seen now from this discussion that not every monomers can be polymerized by ionically, and there is a set of monomers which can be polymerized aninically, and less number of monomers can be polymerized cationically, and there are even lesser number of monomers which can be polymerized by both anionic and cationic polymerization. Whereas, in case of radical, we have seen that all this monomer or these monomers or this can be all polymerized by radical chain polymerization. So, in that case, in that comparison, radical chain polymerization is much less sensitive compared to the ionic polymerization. Now, second characteristics if you want to talk about is that effect of polarity, of the solvent. It is not only polarity, but the capability of the solvent molecules to solvate the ionic species during the chain propagation. Now, as we have seen earlier that a propagation reaction can be written as this. Okay. It is a either a cationic species or a anionic species. Now, this anionic species or cationic species, they are not present alone in the medium, they are always associated with or accompanied by a counter ion. For a positive it is a anion, or a for negative it is a cation. So, this propagating chain are always, or this ionic group are always accompanied by a counter ion of oppositely charged, that always happens. Now, depending on the association behavior of these two species, the active center and the counter ion, the reactivity of the propagating species varies. What I mean that if they are very tightly bound, they are very tight ion pair, then obviously the accessibility of or the reactivity of this ionic center are less. So, the propagating species is less reactive, while if you compare with a situation where they are well separated, they are like free ions. Now, if these are free, then obviously they are more accessible, and the reactivity of these propagating species, ionic propagating species, are much more reactive, or much more reactive compared to the situation when they are tight ion pair. So, it is always preferred that you have a polar solvent. It is always preferred that you do ionic reaction on a polar solvent, because if you have a polar solvent, then these oppositely charged ions will be well separated in the medium, and if they are well separated, obviously the reactivity of the active center in the propagating chain will be higher. So, you have a higher rate of reaction or and eventually higher molecular buildup. Now, often if you use polar solvents, say for example, if you use hydroxylated solvents like say H2O or alcohol, what happens, this reacts, these hydroxylated solvents reacts very fast, very effectively they react with these ionic species and then stop the chain. So, these ionic centers are destroyed with reaction of these hydroxyl molecules H2O or alcohol. If you have a other polar solvents like say ketone, what happens, these ketones do form complex with this ionic species, and then once they form complex, the reactivity of these ionic species are lost. Okay, so, you do not have a effective polymerization happening. So, you require a polar solvent to have these charges separated and ions as free as possible. Similarly, if you use very high polar solvents like hydroxylated solvents or ketone, then the reaction actually gets stopped by reaction of these solvent molecules with the reactive species. So, eventually or practically a low to moderate polarity solvents like say methylene chloride or say a ethylene dichloride or THF tetrahydrofuran or ether or nitrobenzene. So, these are the examples of some of the solvents which have low to medium polarity and does not react with those ionic species. They actually can be used for ionic species polymerization, but these are not very generic in the sense that these solvents also can react with an ionic species as well. So, we will discuss specifically for the requirement of solvents when we talk about cationic and anionic polymerization individually. Now, how this, if you want to write a generic structure of say to write a say cationic propagating species which have say B a cationic reactive center and a counter ion which is represented A minus. And what are the possible states they can be present? One, they can be a completely covalent bonding, covalent bonded. One, two, they can be tight ion pair. These are very tight, there is no solvent molecule in between. So, tight ion pair, or sometimes it is called contact ion pair, or say some people say intimate ion pair, same thing is called in different name. It can be present as solvated. So, solvated, that is 3 solvated ion pair or loose ion pair, or they can be totally free ion pair. Okay, so, these are the possible, depending on the polarity of the medium, this could be the 4 possible association state between these two ionic species. Now, we have given examples of cation and anion here, where the propagating species is a B plus is say the cationic polymerization, the propagating species in cationic polymerization, but it can be true, these 4 states can be true for the other anionic polymerization as well. Now, obviously, with the increase in the polarity of the medium, if you increase the polarity of the medium, this the more polar means the ions get solvated and then finally gets as a the free ion pair. So, as the reactivity of the ionic center, obviously, the free is the ionic center, it gets, it is become more reactive. So, which means, and in some cases these are not present isolatedly, they actually remain in equilibrium, and the equilibrium shifts depending upon the polarity of the medium. So, in this way you can understand that solvents plays, solvent means I mean polarity of the solvent plays a very important role in terms of reactivity of these ionic reactions. And if you compare with radical chain polymerization, solvent polarity actually have no such role to play. In case of radical chain polymerization, you have to only check whether the solvent can solubilize the monomers or the reagent, and the solvent should not participate in the undesired chain transfer reactions. So, this type of solvent dependent reactivity was absent in case of radical chain polymerization. So, third characteristics we can talk about and compare the nature of reaction. Now, these are complex reactions, as we will find out from further discussion that these are complex reaction and they are very fast. They are fast, they are about say 10 to the power 4 to 10 to the power 6 times of the reaction rate of radical chain polymerization. So, they are very fast, and this fast nature of this reaction is due to the fact that the accumulation of these active centers. Now, as we will immediately discuss that in case of ionic reaction, this bimolecular termination, the bimolecular termination by reaction between two propagating species is absent or absent, because there are ionic charge, one cation cannot react with another cation, cationic propagating species and terminate the reactions. In case of radical, what you have seen, that two radical propagating species can react with each other and can terminate it either by combination or by disproportionation. But in case of say anionic polymerization or cationic polymerization, because they are these propagating species are similarly charged, they cannot react with each other and terminate the chains, and as a result there is a huge increase in the concentration of these active centers in the medium, and as a result the reaction is very fast. Whether in case of radicals, we have seen that the steady state concentration of the active radicals is very low, and as a result the propagation was comparatively low, slower in comparison to this ionic polymerization. And as these ionic centers are very reactive, they are very sensitive to impurities, which includes moisture, because they are very reactive, these ionic centers are very reactive, they are very sensitive to these impurities, where you know that radical though radical chain polymerization are sensitive to impurities, but they are not as radical chain polymerization is not as sensitive as case of ionic chain polymerization. And sometimes large effect of co-catalyst are nothing but small inorganic compounds like say H2O can be observed in case of ionic polymerization, which was not the case of radical polymerization. And as the reaction is very fast and complex, this kinetic data are often not reproducible, because this kinetic data is not always reproducible, especially in this case of kinetics, especially in case of cationic polymerization. The mechanism and the mechanism or the kinetics of this ionic polymerization, especially the cationic chain polymerization, is still not completely understood, and research is still underway to understand the mechanism and kinetics of this ionic polymerization, especially the cationic one, because as I said these reactions are very fast and not reproducible. And as I said earlier, this fourth is the termination reactions. As I said that bimolecular termination is not possible, bimolecular termination by reaction of two propagating species is not possible. And so, if you can suppress the other reactions which are chain transfer reaction, if you can suppress those, you can actually keep these chains, these ionic chains as living, because if you can, because the inherent or intrinsic termination reaction between the propagating species are not there, they are absent. So, if you can stop the side reactions which includes the chain transfer reaction, then you can actually make this chain alive, or this polymerization could be living polymerization. That's especially true for anionic polymerization. You will find out in a later discussion that in case of cationic there are other ways which are likely, like chain transfer reactions, but in case of anionic it is comparatively easy to make this polymerization as living chain polymerization. Whereas, in case of radical we know that this termination can be possible by bimolecular reaction of the two propagating species. So, let us now talk in detail about the cationic polymerization. So, let us talk about now again like radical polymerization, any chain polymerization, this cationic chain polymerization we are discussing. So, I should write cationic chain polymerization. So, it consists of 3 steps: initiation, propagation and termination. First, let us talk about different types of initiation reactions. So, different types of initiation reaction, and first one is which is more common is by reaction of monomer with an electrophile. Cr plus, and this electrophile could be H plus, which you can get it from protonic acids. Now, if I write a generic way, H plus plus a generic structure of a monomer, it gives you CH3 CHY cationic species and A minus. Okay, this is the counter, A minus is the counter ion. Now, Hs would be strong enough, this acid should be more strong enough to produce significant concentration of the protonated species, so that it can initiate or react with the monomer, and A minus, the counter ion, should not be very strong nucleophiles, because if it is a very strong nucleophile, then it can react with the cationic groups and make a covalent bond and stop the reaction there itself. For example, if I consider a case of halogen acids like HX and take the generic structure of the monomer, with the reaction, the proton electrophilic reaction, it will form the same initiating species, but because this halogen anion is, say, chloride ion is so strong nucleophile, it will actually combine again and form a covalent bond. So, your reaction stops there, you cannot have the reaction progressing further. So, other protonic acids like H2SO4 or say HClO4 or phosphoric acid, they are used, they can be used because these counter ions are not so strong nucleophile like halide ions, but still this because they are they are also significantly nucleophilic, this cannot build very high molecular weight polymers by say cationic chain polymerization. So, these are limited and the molecular weights are not very high for this proton by this reaction, cationic reaction by this protonation. So, most popular and most important this electrophilic reaction is reaction of Lewis acids. So, that is B with the Lewis acids. I can write a generic structure like MXN for Lewis acid. An example could be BF3, AlCl3, SnCl4, SbCl5, ZnCl2, TiCl4 and so on, or their organometallic derivatives like RAlCl2 or R2AlCl and so on. So, these are the Lewis acid can be used for supplying a electrophyte for reaction with the monomer, but these Lewis acids are seldom used alone. For example, if you take a reaction of isobutylene plus anhydrous BF3 anhydrous BF3, then there is no reaction, but at the moment you add little bit of water along with this makes. So, you have the same reaction with BF3 plus H2O, then is a rapid reaction. So, this is example showing that these Lewis acids which we just showed in the last page, they are often used along with a second catalyst or co-catalyst, which are can be water molecules or some other molecules. We will just give examples in few minutes. So, if you consider this case, the reaction happens like this: BF3 plus H2O makes a complex. Or we can use the other Lewis acids and we can use this alkyl halides as a co-catalyst, and in this case the complex formed is like this. So, this case this is a protogen which is basically proton donor protogen, and this is catanogen which is a cationic species donor or carbocation donor. Now, this is called nowadays initiator, because this is the species which is supplying the H plus or R plus carbocation in this case, and this is co-initiator BF3 or AlCl3, or sometimes they call this BF3 or AlCl called catalyst, and this initiator is called co-catalyst. So, you should be careful about this nomenclature, either you call this as initiator and co-initiator, or you call this as a catalyst and this is the co-catalyst. Now, I can write a generic reaction for this type of reaction. Now, once you form this again react with the monomer and form the initiating species, which let us write in the next page. Similarly, you can write the similar reaction for this aluminum chloride and alkyl halide reactions. This alkyl halide could be say for example, R could be tertiary carbon or could be a triphenyl carbon group. So, this is example of alkyl halides which are used for this co-catalyst or initiator in this reaction. So, I can write a generic equation or expression, say I for the initiator and y z, this is for your co-initiate, I for the co-initiate, this is for the initiator or this is for the catalyst and this is for the co-catalyst, giving rise to a cationic species and a counter ion, this is I, and which then react with a monomer forming the chain initiating species. Now, we are writing K I for this reaction because it has been found out that of these two reaction, this is the two reactions consist of the chain initiation reaction, this is the step which is rate determining step. So, we will consider this reaction while calculating or while determining the or looking at the kinetics of this chain polymerization. Remember, if you compare with the radical chain polymerization, this was the fast reaction compared to the step, the first step where radical was getting generated from the initiator molecule, and we consider that as a rate determining step for radical chain polymerization, but in this ionic chain polymerization this is the faster reaction step where this is the slower and rate determining step. So, for ionic reaction monomer also participate in the chain initiation reactions, where in case of radical monomer was not actually part of the chain initiating expression. Now, the reaction rate also depends on this y z, which is basically the co-catalyst. It also influences the polymerization rate because the activity of the initiation complex depends how readily it can transfer a proton to the monomer, and that in turns depend on the acidity of this co-catalyst. For example, if I consider a ionic cationic polymerization of isobutylene by tin chloride catalyst, then the reactivity of this reaction or the rate of reaction follows Rp follows in the order like this: nitro ethane, nitroethane, phenol, water, which is basically the ranking of the acidity of this co-catalyst. So, basically the type of co-catalyst also influence the polymerization rate, because the acidity of this complex, the activity of this complex depends on how readily it can supply this cationic species, whether it is a proton or in this case it is a proton or a carbocation to the monomer. And for a protogen or the proton supplier, it depends on the acidity of the co-catalyst. Okay. So, it follows this trend, and for the carbocationic generator like RCl, like AlCl3 plus this reaction. Now, this reaction is little complex, the total polymerization rate dependence on this RCl is very little complex, and we will skip the discussion for this course. So, you should just remember that the structure or the co-catalyst also determine the rate of polymerization and also affect the rate of polymerization, and we will now see that obviously the the catalyst or the co-initiator also affect the rate of polymerization. How? Now, Lewis acid, we are talking about this reaction or the initiation is by Lewis acids. So, Lewis acidity of these different metals increases with atomic number. We know that the Lewis acidity follow this order. This Lewis acidity of these different metals increases with the atomic numbers. Now, for a single metal, so if I consider titanium, again the Lewis acidity increases with the oxidation number. So, TiCl4 have a more Lewis acidity compared to TiCl3 than this. So, for if we compare between different metals, is basically the atomic number will determine the Lewis acidity, and for a same metal, its oxidation state increases, the Lewis acidity increases, and also the Lewis acidity for a single metal follow this trend of the ligand. If this ligand, they follow this. So, obviously, if the ligands are fluorine or chloride, they have much more Lewis acidity compared to if the ligands are. This is from your basic knowledge from inorganic chemistry, ABOC knowledge, and this is from the discussion we know this is the strongest Lewis acid, and but it is not always we use this, though it is a very strong Lewis acid. For all the cationic reaction, we do not use that as a catalyst or the co-initiator, because there are other complications. If the reaction rate is too fast, then the side reactions also come in the picture, the side reactions also increases. If the side reaction rate also increases, then again the problem of molecular buildup comes. So, though this trend is there, now while choosing the catalyst or the co-initiator, it is not this general trend is always followed. You have to keep the other factors in mind as well. So, we talked about the initiator reaction with by this reaction of the monomers with the electrophile. Now, there are other initiation reactions, other initiation reactions. For example, halogen can be reacting with a more acidic Lewis acid and gives rise to say cation, halogen cation. This can be initiation can be done by photo initiation of oleum salts. It can be done by electro initiation, where a cationic species is formed by electrolysis of any species present in the medium. Or it can be done by ionic ionization radiation, like in the case of radical. the initiation can be done by ionization reaction. So, these are the other possible ways of initiating a cationic polymerization, but as I mentioned in earlier, this the generic examples which we gave in this page, these are the most common example of or the most important initiation reaction. So, when you talk about kinetics or energetics, we will consider this generic initiation step and also consider this initiation step for the discussion, because this is the most important of the initiation steps we just discussed. So, let us now discuss the propagation step. Propagation, we have already seen the different types of initiation possibility, and as I said, we will consider the generic case I just showed there. So, this was the initiation reaction. So, you have this initiator co-initiator complex which start the chain initiation. I write this in the next page. It can react with the M and start the chain propagation reaction, and I can write a generic expression of this in this way, plus M K P n plus 1 n plus I z minus. If y is H, the protogens, we can write H m n m plus I z minus for examples that BF3 water case, I can write this is a proton donor. So, I can write this is a reaction of isobutylene catalyzed by this is a reaction. Just recall from your earlier discussion, I am writing the propagating reactions here. This on reacting with isobutylene with produce the okay. So, these are the examples of the propagating steps, and sometimes this propagation reaction could be complicated, and because of this 1,2 hydride shift, and but that is not very common. I will just give you example when these propagating steps could be little complicated, and by hydride shift or methide shift, and that is applicable for say propene or one alkenes. Take example Now, this can undergo a hydride shift and from this carbocation. So, as a result, more complicated products actually form when there is this type of hydride shift or some cases methide shift, some cases shift 1 to methide shift. If this happen, the reactions become very complicated and we call that sometime isomerization polymerization as well, but this is not common. This is this applicable to some monomers, the example we give. Most common propagation steps are in this page what we just discussed now, and as you can realize that the rate of propagation will depend on the solvents. We discussed in length the effect of solvent polarity, and if the polarity of the solvents is high, then this ion pair will be more towards a solvated or free ion pairs, then the reactivity of this cationic species will be higher. So, the rate of polymerization will be higher. Now, let us see some data, real data to convince that understanding. Say let us take example of styrene polymerization of styrene by chloric acid HCl4. Now, solvent is a mixture of CCl4 and ethylene dichloride. This is your dielectric resulting dielectric constant, and this is your Kp liter mole inverse second inverse. So, if you have pure CCl4, obviously this is more non-polar, dielectric constant is 2.3 and the rate is low. When you increase the polarity by adding ethylene dichloride, dichloroethane, you say in 40-60 mixture, your dielectric constant goes up, your reaction goes up. If you consider further 2080, 7 and this is 3.2, 3.2, 0, 100, 9.72 and this is 7. So, this is the data to convince you that if you increase the polarity, which is given by here dielectric constant, the rate constant or the rate of the polymerization reaction increases. So, we just discussed the propagation steps. Now, let us talk about different possible termination steps in cationic chain polymerization, and as once more time that it cannot termination does not happen by bimolecular reaction of the propagating species, and generally the termination happens by transfer reactions. For example, one beta proton transfer to either monomer or counter ion or say polymer itself, solvent or some impurities which is present, or a transfer agent like the case of chain radical polymerization. We talked about the chain transfer is possible, And for example, if we consider the beta proton transfer to monomer, I can write K transfer monomers just like the radical polymerization. If we consider the same examples for isobutylene polymerization by BF3 and H2O, this can transfer a beta proton to the monomer and can form this, and plus there are two beta proton, one is here and one is this hydrogens. Okay. So, one of depending on which proton is leaving, you can get actually two structures with double bond. If this comes out, then you get a chain end with CH 2 if this proton goes out, and if something one of the protons goes out from there, then you get CH. Okay. And that is possible, these are possible for other monomers where these two types of double bond is a possibility. For example, like you have a alpha methyl styrene. Now, in case of say the monomers like styrene, where you always gets only one possible double bond, because there is only one possible beta hydrogen to be eliminated. So, this is very common, this is very important termination process, and it could be, this termination could happen to one of any of the other agent as well. We just gave an example with the monomer, and what we will do in the next lecture, we will talk about the other termination possibilities, and we will discuss the kinetics and the energetics of the cationic polymerization, cationic chain polymerization, and then also discuss the characteristics and other features of anionic chain polymerization.